Okay, we got our result from last time having to do with a falling mass that is attached to a core that's wrapped around a massive pulley that has friction at the pin. And from the details we got there, we found that the angular acceleration of the pulley was 16.33 radians per second squared. And now we want to answer the next parts of the question. If part B asked, if the mass is released from rest, how long does it take for the mass to fall 1.5 meters? How long does it take for it to move 1.5 meters down? That sounds like a kinematics question, and to answer it, we just need to know what the acceleration is of this. Remember, we called plus y downward from it, so we want to know the y acceleration. And we found out earlier that the y acceleration is equal to r times alpha. This came from a tangential is r alpha applied to a point on the edge of the wheel, and the tangential acceleration of that point was the same as the y acceleration of this block down here because they're moving in the same direction. So if we use that, ay is equal to r times alpha. R is, in this case, the radius of the pulley, and alpha is the number we just got. The radius of the pulley is 0.2 meters, so plugging that in, we get ay is 3.267 meters per second squared. Now we've got that acceleration, we can use it in a kinematics calculation, and because the acceleration is constant, and so we look for one that where we know the distance it moves and we want to know the time. So that's like y versus t. Let's grab the y versus t kinematics equation, and what we know is y minus y0 is 1.5 meters, and vy0 is 0, and we want to solve for t. So plugging that in, here's the equation we get. Multiply the other stuff to the other side, and take the square root, and we get t is a little bit less than 1 second in this case. All right, let's go on to the next problem solution. Here we've got a uniform rod which we released from rest at this horizontal position, and it rotates freely about this pin, and we want to know what is its angular acceleration as it zooms past this position, which is 30 degrees below horizontal. And the way we're going to get that is, well, how do we get alpha? Just like how do we get A in any case where someone doesn't tell it to us, we use F equals ma. So here we're going to use torque net equals I alpha. And in order to figure out what the torque is, well, what torque is causing this thing to rotate faster and faster about the pin? It's gravity. And so applying the net torque equals I alpha, the net torque is just the gravitational torque. And we need to calculate the gravitational torque to plug into I alpha and then solve for alpha. So let's work on getting the gravitational torque. Remember, gravity exerts a force on all little bits of mass all the way across the rod, but one of our simplifying principles is that we showed, for the purposes of calculating torque, we can pretend that the entire mass is concentrated at the location called the center of mass, and the center of mass for a symmetric object is always at the center of symmetry of the object. So in this case, we're going to pretend that the full mass m, that's 2 kilograms, is located at the center of mass, and that gravitational force is being applied just right there. And so to calculate the gravitational torque, we can use the magnitude of the force times the moment arm. And remember, the moment arm is you draw the line that contains the force that's being applied to the rotating object, and you look for that shortest perpendicular distance. So this is the moment arm right there. And we can get that from this little right triangle there. The hypotenuse is 0.5 meters. So because it's halfway down the rod. So 0.5 times the sine, 0.5 times the cosine of 30 is this distance right there. That's what we would call the moment arm. That's 0.433 meters in this case. And so I can plug the 2 kilograms and that results into here and get the gravitational torque on this at the location 30 degrees below the horizontal is 8.487 Newton meters. And now the whole point of doing that was to put it into torque net equals I alpha. Torque net is equal to just the gravitational torque in here. There are no other torques being applied. And so to solve for alpha, we just need to figure out what I is, and we can go to our table of moments of inertia and look for the one for a rod pivoted about one end. So in this case, that's the moment of inertia is 1/3 ml squared, where L is the length of the rod. So plugging that in for I is 1/3 ml squared, and then dividing that out from the alpha side to get alpha, we get 12.73 radians per second squared is the angular acceleration of this at this point, right as it's passing that position, 30 degrees below horizontal. Okay, let's go on. We've made some good use out of that simplifying principle, and here again is the principle. I know this is kind of a busy slide, but it's just supposed to remind us that if we have a rigid body, that's this teardrop-shaped object, rotating about a fixed axis, shown here in red, then we can pretend that all the mass is located at the center of mass, and so that full weight force is just being applied there for the purposes of calculating the torque. That's a great simplifying principle that saves us lots of work. We're going to show that there are some other simplifying principles when a rigid body is rotating about a fixed axis. Not only is the gravitational torque able to be calculated by pretending all the mass is concentrated at the center of mass, the same thing is true about the potential energy. And what I mean by that is, let's imagine this object is rigid and fixed to rotate about a fixed axis, shown here. And as it rotates, for example, down, the gravitational potential energy is going to change. So here it is, it's rotated to a position about this fixed axis, the later position I've shown in kind of a pink color down here. The problem is we want to use what we know about gravitational potential energy, and that's mg times y. Remember, that was our formula for gravitational potential energy near the surface of the Earth. So the change in potential energy would be the change mg times delta y. But the problem is all the different bits of m on here, I've just shown mass m1 and m2 as particular parts of the gray one here. m1 moves down to this position. m2 moves down to this position. m3 and m3 near the axis, it would only move a small amount. So all the different m's are moving down by different amounts. But undaunted, let's go ahead and try to calculate the change in the gravitational potential energy in between the gray position and the pink position. What we do is calculate, well, let's first just calculate the change in potential energy of mass m1. That would be m1 times g times delta y1, where delta y1 means the change in the vertical coordinate of m1. Okay, that's just the potential energy change of m1. Now we've got to add in m2's term to that. m2 also has some change in potential energy, and its delta y2 is going to be different than m1. And we got to do that for m3 and m4. There may be 1,000 of them we have to add up to get a good approximation for the change in potential energy. When we do that, we can now look at this mess and say, well, you know, at least one thing we can simplify is there's a common factor of g in all these 1,000 terms. Let's factor it out on the right-hand side. So I factor the g, common factor of little g, out on the left-hand side in this case. And because what's left in the parentheses kind of looks like it's related to the y-coordinate of the center of mass, I'm going to take this expression and multiply by the total mass of the object and divide by the total mass of the object. And of course that doesn't do anything. We're always welcome to multiply by m as long as we divide by m in the same expression. Now, if you look at the ratio on the right-hand side of this, this looks like the change in the y-coordinate of the center of mass. In other words, the y-coordinate of the center of mass is m1y1 plus m2y2 over the total m. And if we did the change of that, we would just get deltas up in the numerator. So what is on the right here is just the change in the y-coordinate of the center of mass of the object. So that looks like a simplifying principle. How do we use it? Well, if we know where the center of mass is, and often we will because a lot of objects are nice and symmetric, and so then we know the center of mass is at the center of symmetry. Here I'm imagining the center of mass is at this location here, sort of near this protruding point there. So it moves from here down to here. All we have to do is figure out how far it moves down vertically in space, and multiply the total mass of that object times g times the change in y coordinate of the center of mass. Okay, so that means the gravitational torque and gravitational potential energy can both be calculated by pretending all of the mass that's really distributed over the body is concentrated at the center of mass. That's nice. Here is a third simplifying principle. If an object is rotating with angular speed omega, the kinetic energy also seems like it would be a nightmare. Because look, M1 and M2, if we have an M3 that's near the axis, they're all going to be moving at different speeds, right? The masses that are farther out are going to be moving really quickly as this rotates at some angular speed, whereas the ones near the axis are going to be hardly moving at all. And all we know about kinetic energy so far is 1/2 mv squared. So if we really want to figure out what the kinetic energy of this object is, we got to add up 1/2 mv squared for mass m1 plus mass m2, and maybe we divide this object into 1,000 little pieces and do that for all 1,000 pieces. We add them all up, 1,000 different terms there. That's why it seems like a nightmare, but let's continue undaunted. We remember, hopefully, the relationship between the speed of a point on an object and its angular velocity. That was one of our relations between linear and angular relationships, and the relationship was v equals r omega. So the speed of mass m1 is r1, that's the distance of m1 from the axis, times omega. I'm going to replace v1 by r1 omega there. And omega, well, there's only one omega for the whole body. I don't need to put a 1 on it because it's the same for everything. Speed of m2 is r2 omega, okay? And I'm going to do that for all 1,000 terms. And then I'm going to square these out. So if you have a product of things squared, that's just the squares of the individual factors. So that's r1 squared times omega squared and so on. And then looking at all these terms, I've got some common things to every term. There's a 1/2 in every term. I'm going to factor that out on the left. And there's an omega squared in every term. I'm going to factor that same omega squared out on the right. And I've shown that here. What's left after I do those two factorings is shown in green in the parentheses. And that, by definition, is the moment of inertia of the object. The sum of all the masses times their distance from the axis of rotation squared. So this is just I for the object for rotation about that axis. So what we've shown is that for an object that is rotating around a fixed axis at angular speed omega, the kinetic energy is 1/2 I omega squared. And that's a great simplifying principle, because even though all the different parts of the object are moving at different speeds, we only have to calculate one thing, and that's really nice. So let's practice using those simplifying principles and see how we can use them in an energy calculation. Here's an add-on to the previous problem. It's not really in your worksheet, but I just kind of did it in here, so let's do it together. Same situation as before. We release a rod from rest horizontal. It rotates freely about the pivot at the left end, and we want to know at the position shown here, 30 degrees below the horizontal, what's the rod's angular speed at this position? How fast is it rotating there, right? It wasn't rotating at all when we let it go, but it sped up. What's the angular speed at this position? Then we want to know the linear speeds of a couple of points on it. Okay, let's concentrate on that first question. To answer that, we're going to use energy methods. We're going to say our system is the rod plus the Earth. And the rod-Earth system, where gravity is internal, is going to be changing its potential energy as mass starts to go down closer and closer to Earth. There's another force on this rod. We've got to have, even though the pin doesn't exert any friction on this thing as it rotates, the pin has to be pushing up on the rod. Otherwise, the axis of rotation wouldn't stay fixed, right? If we let this go and there were no pin pushing up on that point, the whole rod would just fall straight down and stay horizontal. So in order to have a fixed axis, the pin has to be pushing up on it. So we'll call that pin force on the moving rod external, but it doesn't really matter. The pin force doesn't do any work because the point at which the force is being applied to the rod isn't moving as the rod rotates, right? Because that point on the object is really fixed in space. Okay, So our only external force is that pin force, so I'll say the work done by the axis pin. The change in kinetic energy, let's use our new expression here, and that's 1/2 I omega final squared minus 1/2 I omega initial squared. That Cm shouldn't be in there. This should just be a plain old I right there. So that's the change in kinetic energy, plus the change in potential energy is mg times the change in the y-coordinate of the center of mass. So let's try to figure out what those are. That axis pin, as we said, doesn't do any work because the point at which the pin force is being applied to the rod is not moving. So that pin force, even though it's important, it's not doing any work in between the initial and final. To calculate the change in the y-coordinate of the center of mass, well, again, this is a symmetric object. Its center of mass is always at the center of symmetry. That's halfway down the rod, ½ meter from the pivot point. And therefore, the center of mass started out up here, and it's going down here. The change in the y-coordinate of the center of mass is just this height right here. We can get that by looking at the little right triangle. That would be 0.5 meters times the sine of 30 degrees is this change in height of the center of mass. Okay? Let's plug that in the next step here. It's the change in the y-coordinate of the center of mass is negative because it's going down closer to the Earth. This is how far the center of mass moves down. And also, I won't bother going back to show it, but from our table of moments of inertia, the moment of inertia of a rigid rod rotating about one of its ends is 1/3 ml squared. So I plugged that into the first term here. And omega initial is 0 because we released it from rest. And I'm going to call initial up here and final down there. All right. Let's simplify a little bit more. The m's can cancel out here because there's we can divide both sides by m, and the m will just go away. And also L in that moment of inertia is the length of the rod, so we can plug in 1 meter for L and cancel the m's. Now we know everything in that expression except omega final. Plugging it into the calculator, we get 3.83 radians per second as the speed of the angular speed of this, the rate at which it's rotating about the axis as it moves through that point right there. Next question. What is the speed of the right end of the rod at this position? In other words, how fast, in the good old-fashioned linear sense, how fast is this point moving at that location, at that position? And the way we're going to do this is our relationship between linear and angular velocities. We now know the angular velocity. We want to know the linear velocity of a point. We have to be careful here in interpreting r. What it means is we want to know the speed of this point. The relevant r is how far that point is from the axis of rotation. So in this case, r is the full 1 meter, and the omega is what we just found in the part above. So multiplying those together, we get the speed of this point is 3.83 meters per second. Now, the next question is, what's the speed of the center of the rod? The center of the rod is not speeding. Its speed is not as big as the speed on the end. In other words, the points near the axis are moving hardly at all, whereas the points out here are moving at a pretty good clip. So even though we're going to use the same relationship, V equals R omega in the second case, it's got to change, and the omega isn't changing. There's only one omega for the whole object, but it's the R that changes. We now want to know the speed of this point right here. So the relevant R is how far that point we're interested in is from the axis of rotation, and that's 1/2 meter in this case. So multiplying that out, we get half of the speed of the point out here is how fast this one's going, 1.92 meters per second. All right, let's take a little break now.